The new chapter will be about RC series circuit. Let me just go back to the previous page and check just the title. So as you can see here from the title, we will talk about a circuit, which is a series circuit containing a resistor and a capacitor. And the square signal that we'll be working with, or the constant voltage source that we'll be working with, will let us show how a capacitor works or functions during its charging phase and discharging phase. Usually we use the symbol of a capacitor like this one. It's similar to a battery, but instead of having two different lengths for the poles, the capacitor is made up of two same length poles. So it functions like a battery, but the main difference is that the capacitor will provide energy or will provide power for a short interval of time. Usually it's less than a second. What are the main functions for a capacitor? Usually, if you go back to the previous year and check more details about the capacitor, you will see that, as you can see here, they said that the capacitor is an electric component consisting of two conducting surfaces facing each other and separated by an insulator. So usually the symbol that we will see here, it represents two, if you want, metallic conducting spheres or plates, depending on the shape of the capacitor, with some insulators or a material that works like an insulator in between. We have different shapes for capacitors, like the cylindrical or the flat parallel plate capacitors. They will function similar to each other, but the shape is just different. And they said here that capacitors are important in electric and electronic circuits. Capacitors are found in a radio or radios, TVs. They are used in burglar alarms, usually the alarms that are placed in some factories or other maybe buildings. The flash unit of a camera, once you take a maybe using your phone also, once you take like a picture using your flash, the moments that the flash provides this light, it takes about milliseconds. The capacitor will be doing this job. It's not the main battery, okay? So the capacitor can provide high energy, high current, sometimes high voltage depending on the circuit, but for a short interval of time. Usually it's less than a second. They have many forms and styles such as those in figure 2. All right. So let's try to start with the first part, which is the charging and the discharging of a capacitor. I'm not going to use the same experiment here that they showed. Somehow it's not complicated, but there is a lot of information mixed together. So I'm just going to put them in order on my own way. Okay, let's start here. Usually, in order to use a capacitor, we need a circuit for the capacitor to be charged or to be discharged. Let's try to draw a simple circuit. I'm going to use a circuit similar to your books, so that in case you studied using your book, you will get the same results or the same figure. So let's take the first title. Let me show here the title. I'm going to write charging and discharging of a capacitor. Okay, so this is the first title that we will be working with. Let's assume this figure. Sure, we need a capacitor, we need a resistor, and we need a voltage source. I'm not going to draw a generator source. I'm just going to draw a DC battery to make it easier for us at the moment in order to study a capacitor. I forgot to add the resistor. Let me just do it here. So this part will be the charging phase. As you can see in the charging phase, we need a battery or a source of voltage. Okay, so the generator is provided here. Here I'm just showing a DC battery, not a generator itself, but it works like a generator. This is the resistor, and this is the capacitor. We will name it as C. I'm going to provide the closed shapes and similar figures as that in the book. Usually we need to specify a positive sense as usual. Later on, we will see why we need that. Let's take the positive sense similar to that of the current flowing in this circuit. First of all, in the charging phase, we can assume that the main voltage of this battery, so let's try to write some given here. So given that the battery or in between brackets, we call it the G or generator. Okay, generator G. Is okay. Let me write given, highlighted, and then here. This is the first point. So this is the battery or G with an EMF, electromotive force, E. So E represents the main voltage of this battery. We usually call it E, which is EMF, or if you don't know the meaning of EMF from grade 10, it's electromotive force of this battery, or in general, it's the voltage of the battery. So the maximum voltage that this battery can provide is capital E, okay? Hope you got my idea. So for this battery, the voltage will be maximum E. All right, so during the charging process, the initially the capacitor will be, so at t equals 0, at t equals 0 seconds, the capacitor will be uncharged. So the capacitor will be uncharged. So if I want to know the voltage of the capacitor, U of the capacitor will be initially equals to 0 volt. Is there any question till now? I will just wait seconds to check if you have any problem before I move on. Great. So initially, the current will start flowing from the positive terminal of this battery. How a capacitor works? Usually, the dielectric will provide or will never allow any of the electrons to move or jump from one plate to the other. So let's try to take some notes about the capacitor. Usually, if we want to go back to the previous year and check the information about the capacitor, I'm going to write it as a note here. Note. Okay. This is a capacitor. These, we call these as parallel plates or plates in general. They are conductors. So they allow charges to settle on them. And in between these two plates here, there is a dielectric. Dielectric material, maybe it's plastic, sometimes it's air, sometimes it's like papers, anything that doesn't allow current to flow. So this is in general a capacitor. It's made up of two parallel plates or plates in general these plates allow the charges to be accumulating, and in between there is a dielectric. How this capacitor allow current to flow in a circuit? The electric field created inside a capacitor is the main reason for current to be flowing. So electric field lines will be created by the charges itself. Always and always the electric field lines will be generated from the positive charges towards the negative charges. So it's like how somehow similar to the flow of current in a circuit. Electric field lines will be created in between the terminals of a capacitor. So if I want to draw the terminals again in a big or zoomed figure, if this is a capacitor, and let's say that this is the positive charge on the left side of the plate, and these are the negative charges on the right side. Now electric field lines will be generated from the positive towards the negative side. We symbolize them by capital E vector, and we call them electric field lines, or in general, electric field created by the charges. So this is the reason how current will continue flowing in a circuit. Okay, what will be happening here, if we want to go a little bit, to zoom a little bit here into this figure, the free electrons of the plates on the capacitor on the side close to the positive terminal of this battery. So here we have a positive terminal of the battery, and here this is the negative terminal. And usually we talk about the electrons moving or circulating and not about the positive charges. So once we want to talk about the charges, we don't care about the positive charges, we care about the negative charges. So each of these plates, initially they will be neutral. So each plate will contain positive and negative charges. Once the circuit or the switch is closed, and this, let me just show here a switch, okay? Assume to have a switch. Once the switch is closed, electrons will be attracted by the positive terminal of the battery. So they will try to move on towards the positive terminal of the battery. So electrons from the left side of this capacitor will be attracted by the positive terminal of the generator. Some of these will be transferred to the positive terminal, and then the same plate will be positively charged. Let me repeat the process here. Assume that this plate contains positive and negative. So I'm just showing some positive charges on the left plate and some negative charges. Since we connected the positive terminal of the battery here to that plate, then the electrons will be attracted. So electrons will be moving towards the battery, towards the positive terminal, since minus and plus attract. Then here I can erase these minus charges, sorry. So I can erase the negative charges, and instead of them, I can just show nothing here. Okay, so here I can just erase the negative charges. I'm just providing an exaggeration for the ideas here. So this plate will be somehow positively charged due to the excess or due to the deficit of electrons or due to the excess of positive charges. So once these electrons try to circulate towards the battery, they will move to the other side of the capacitor. They will move from the positive side of the generator towards the negative side, and they will come here to the other side later on. So the capacitor will be charged like a battery. At the end of this moment, it will be positively charged, and the right side will be negatively charged. So this process, with time, the capacitor will be fully charged. We don't care about these details, but I'm going to provide these details for the first time only. But later on, we will not enter into these details deep like this time, okay? So let's make the circuit again clear and try to make it simple. I provided these ideas just for the first time. Okay, what we care about, I'm going to write it here so that you can keep the important information in your mind and in your copybooks. So we said the important point is that at t equals 0, initially the capacitor will be uncharged. So initially At t equals 0, the capacitor is uncharged, and the voltage of the capacitor will be 0 initially. Okay, later on with time, if I want to apply here the law of addition of voltages, we can write like this. We can say U of the generator equals U of the resistor plus U of the capacitor. This is the law of addition of voltages, law of addition in a series circuit. So now initially we said that the initial voltage of the battery is E, and you can see that E is written here, okay? Equals UR, but we know that the voltage across the resistor using Ohm's law is I times R. So instead of UR, I'm going to write I times R. This is Ohm's law. Plus, initially at t equals 0, the capacitor is still uncharged. So this one will be 0. So I'm going to write here as a 0 voltage. Now we can find I. I will be equal to E over R. And this I is the maximum current, implies that I equals to I maximum equals to E over R. So initially, the current will be flowing in a maximum intensity, maximum value. All right. Now, as time goes on, let me just take copy for this part. As time goes on, the capacitor will be charged second after second. So after a certain interval of time, the capacitor will be increasing its voltage. So as time goes on, the voltage across the capacitor will be increasing. And as you can see, using the same formula, if I write the same formula again here, let me just show you the main formula I'm talking about here, this one. If I try to copy it again, so UG equals UR plus UC. If this one is constant, so UG is constant, it's E. And the capacitor is increasing its voltage. So UC is increasing. Now you know that UR will be decreasing, or in other words, I times R, which is Ohm's law, tells us that the current will be decreasing to keep the value constant, to keep the equation correct. So now as time goes on, the current will be decreasing. The voltage across the capacitor will be increasing, and the current will be decreasing. Okay, finally, the last step at electric equilibrium. Let me make this small handwriting smaller. Okay, at electric equilibrium, the capacitor will be fully charged, and it will gain the same voltage as that of the battery, or as that of the voltage source. Then UC will be equal to maximum, which is E, capital E, which is the main voltage of the battery. implies that if I try to apply the same rule, UG equals UR plus UC, UG is E, and the capacitor now is fully charged, then UR will be equal to 0 to keep the equation correct. Implies that I will be equal to 0. No current will be flowing at that moment. So if we want to recap the information till now, we said that initially the capacitor is 0. It's totally empty. With time, the voltage across the capacitor will start increasing till it reaches maximum value or maximum voltage. If I want to draw this in a small graph, I can show it here. Let me try to show the graph somewhere. Okay, it's better to draw the graph here. Look, please. Okay, this one will be the time. And here we'll show the voltage. Sure, we'll be talking about the voltage of the capacitor in general, U. If I want to draw the voltage across the battery will be constant voltage. Let me just show it up to 4 divisions as a... Okay, so let's write here. This is U generator, and it's equal to E, the maximum voltage. While if you want to draw the capacitor will be increasing its voltage in this way. So it will start showing an increase in the voltage till it reaches its maximum. So this curve represents UC, U of the capacitor. So as time increases, the voltage of the capacitor will be increasing. Initially, the current will be maximum. Finally, the current will be minimum. So here, the current I will be equal to 0 at the end once the capacitor is fully charged. And initially, in the initial stages, I will be equal to maximum. It's similar to a tank that you want to fill it with water. Initially, once the quantity of water in this tank is almost 0, the water will be entering in a big quantity. After a certain interval of time, once the tank is fully or filled, totally filled with water, then we can say that the current will start decreasing to reach 0 intensity. Okay, I'll wait a little bit to check if you have any questions. I will keep the screen like you can see here. If you have any questions, I'll wait a little bit before starting with something else.
Always we write the same steps. We start from t equals 0 till it end, or حسب السؤال.
Depending on the question, they will ask you maybe at t equals 0 what will happen, or what's the current initially, or what's the current finally, or they will ask you in a special detail or in details.
But
at
the same steps.
Yes, it will be repeated.
Thank you.
Welcome. Okay, great. Now I'm just going to draw a graph below this one to show the current at the same moment. Okay, so let's take the same graph, similar one. Let me show it here. Okay, so I'm just trying to draw the same graph. And let's say that here we want to show the current in general, or the voltage across the resistor, since it's always opposite. So this one, the red figure now, the new one, shows or tells you the voltage across the resistor. It's totally not accurate, but here it tells you the voltage across the resistor, or in general, it tells you the current. So it tells us about the current. Since U R equals I times R, this one is constant. So this one will be related to that one. So the voltage of the resistor tells you about the current in the circuit. So as much as the voltage here within the first graph increases to reach its maximum, then the current will start decreasing to reach its minimum till it reaches zero value. So UV, and also this one is time. Okay. In general, if at any moment we want to find the current at any moment, using the general rule, we can, let's write here, if at any moment we want to find the current in the circuit, then we can just write again the main formula, which is U generator equals U resistor plus U capacitor. U generator, which is E, U resistor I times R, and U capacitor, which is UC. Now we can find I times R, or in general, IR can be written E minus UC. And then finally, I will be equal to E minus UC over R. So as much as the voltage UC increases, current I decreases. It's inversely proportional. So this is the general rule for the current. It's not to be memorized, just depending on the circuit, you can find this relation. All right. Now we'll move into the discharging phase of a capacitor. Let me just copy the same title. This one. Okay, I'm going to write it again. Discharging phase. Okay, in the discharging phase, we assume that the circuit is made up without a voltage source. So UG is 0 now. There is no voltage source, so I can just draw the same circuit without a voltage source, or no voltage source. So I can just take the same circuit, this one, but without drawing any generator, like a capacitor and a resistor. So as if I'm just showing this circuit. Note that during the discharging phase, the current will be flowing in the anti-clockwise direction, since the electrons and the protons will be accumulated in the opposite way of that of a battery, so that the current will be flowing in the opposite direction. So I will be flowing anti-clockwise. While in the initial phase, if you go back to the circuit, you will see that the current will be flowing from the positive terminal towards the capacitor, which is clockwise. So note that the current always and always during the charging and discharging is going to be opposite. Now, if we want to start with the initial process, we can say that the capacitor is being discharged in the resistor. So the resistor is discharging all the capacitor. And note that the energy taken by the resistor will totally be changed into heat or thermal energy. So it's just going to be lost. Here the capacitor, if I want to write as a note, the capacitor acts as a generator The other idea is that the resistor is discharging the capacitor. Sorry. So it's just taking the energy from the capacitor, and the voltage across the capacitor will start decreasing from maximum value E to 0. So finally, or the final idea is that the voltage across the capacitor will start decreasing from capital E, which is its maximum value, to reach 0. And sure, once it's being totally discharged. So once it's totally discharged, the voltage across the capacitor will be 0. If we want to write the same equation, we can write it like this. U of the generator, which is 0 right now, we don't have a generator, will be equal to U resistor plus U capacitor. Resistor is I times R plus UC. If I want to find I will be equal minus UC over R. The negative sign tells you the capacitor is being discharged and the current is negative, so it's going to be moving in the anti-clockwise direction. At T0 equals 0 seconds, you see the capacitor will be maximum fully charged, implies that I will be equal to minus E over R. I'm just substituting this formula, okay? So you see I'm just writing it here, which is E over R. And this value is the maximum value of the current initially. So in the discharging phase, the current will be maximum initially, and it's going to be minimum finally. Assume that it's similar also to a tank filled with water. If you are taking water from it, it will give you maximum amount of water initially, and once the tank is empty, the water flowing will tend to 0. Okay. Finally, the capacitor becomes completely or totally discharged. Then U across the capacitor will be equal to 0, and I will be equal to 0 also. And if we want to draw the same graphs, we can show it like the figure that I'm going to draw at this moment. So this is the voltage U in volts, and this is the time. And initially the capacitor is fully charged. So I'm going to start from the maximum to reach its minimum after a certain interval of time. So here it's totally discharged. And initially this value will be E. And this graph tells you the voltage across the capacitor. If you have any question, let me know, please. Concerning the current, it's similar to that of the previous curve. The current will start maximum and it will end up with 0. So in both curves, the current will be the same, but just the direction of the current will be changed. Nothing more than that. So if I want to draw the graph for the current, I will show it on the negative side, not on the positive side, to show that it's going to be moving in the opposite way. Nothing more than that. Okay, I'll wait a little bit for you to check if you have any comment, any question before I continue.
The current has the same graph.
No, look here. If I want to show it here in similar graph, the current will take the same graph like this one. Okay, I'm going to end the meeting and start a new one.